Hello and welcome. Today we're going to be discussing our first day of section 2.7, which is on dilations. In this first paragraph, we have the definition of dilations. A dilation is a transformation in which a figure is made larger or smaller with respect to a point called the center of dilation. In the image to the right is a really good illustration of dilations. Either the red or the blue figure could be the original, depending on if we started with the blue and dilated by a smaller number to decrease the size, or maybe we started with the red and dilated by a larger number to increase the size and end with the blue. Either is possible. Regardless, this blue point is our center of dilation. For this example, we'll go ahead and assume that the red figure is the pre-image, or the one we start with, and this blue figure is going to be our image, or our ending figure. If I start with the blue figure and want to dilate it, I'm going to measure the distance from the center of dilation to each of the vertices, and multiply that by the desired factor. For example, if I want to dilate by a factor of 3, I would take this red distance, measure it, and then just extend that line 3 times as long to end at the new vertex of my figure. So this distance now, I'll draw it in blue, is 3 times as long as it was when I measured from the center of dilation to my pre-image. To find the other vertices, we would simply repeat this process. From the center of dilation to this bottom vertex, I would measure and multiply that length by 3, and then just extend my line to 3 times as long, ending at my new vertex. So again, that blue segment that I just drew would be 3 times as long as the original. That might not be accurate in regards to our drawing, but this is just how it would work in general. In example 1, we're not going to be worrying about factors of dilation. All we're going to do is decide, is there some center of dilation that we can use to obtain the blue figure from the red figure? To do this, we're going to work our way backwards. In this illustration above, we have a center of dilation, and when we connect that center of dilation with each of our vertices, we can then extend those segments to reach the new vertices of the image. Well, instead of starting with the center of dilation, we're going to connect our vertices and work our way backwards. If those segments all intersect at the same point, then that point would be our center of dilation, and the figure would in fact be a dilation. This is how it would look. I first draw a segment connecting the red figure to the blue figure, and I'm going to draw it longer than I need because, again, I'm hoping that I have some center of dilation that's out here to the left. I'll repeat that for the vertex that's on the right of these triangles. Connect them as accurately as you can, and it would look something like that. So if my third line crosses through this same point that these two cross at, then that is my center of dilation, meaning that the blue figure is in fact a dilation of the red. Connecting these third vertices, that line does in fact go through the same point. So this point here would be our center of dilation, and our answer to this question is yes. The blue figure is a dilation of the red figure. For letter B, I'll repeat this process, connecting my vertices from red to blue. It doesn't look like the first two intersect, meaning when I draw the third one, that's not going to intersect with the other two either. So for letter B, this would be no, it is not a dilation because those segments do not ever intersect all at the same point. Go ahead and take a moment to please pause the video and try numbers 1 and 2 on your own. In number 1, when I try and connect my vertices, the corresponding vertices are horizontal to one another, so when I start connecting them, my lines don't all intersect at the same point. All 4 of these lines that I'm drawing should cross at the same point, but in fact they don't. So this would be a no. The blue figure is not a dilation of the red figure. For number 2, I'm going to repeat this process and begin connecting the vertices of the squares. Because they are so similar in size, I'm going to have to draw my lines much longer than I did in previous questions because they won't come near each other for quite a ways. As I'm connecting, it does look like they should intersect somewhere out here. Now my lines aren't perfectly straight and that's okay. But if we did draw them the way they should be drawn, they would probably intersect in this area. So our answer for question 2 would be yes. The blue figure is a dilation of the red figure. On our next slide, we're going to be talking about dilations graphically. In a dilation, the original figure and its image are similar. The ratio of the side lengths of the image to the corresponding side lengths of the original figure is the scale factor of the dilation. Looking at our graph over here, if the origin is my center of dilation, I can take the distance from the origin to point A and count it to find that it is 2. Going from the origin to A prime, this is a distance of 6, meaning all we did is we took that original distance and we multiplied it by 3 to obtain the new distance. I can look at the horizontal values as well. From the origin to point C, that is 2. From the origin all the way over to my new C or C prime, that is 6 units, meaning I took that shorter distance and I multiplied it by 3 as well. Well, if we look at the actual side lengths of the triangle, the side length AB has a distance of 2, and the side length A prime to B prime has a length of 6. So those side lengths were also multiplied by that factor of dilation. From B to C, if we look at that distance, we find it's a distance of 2. From B prime to C prime, we see that that's a distance of 6. And again, we multiply by that scale factor of the dilation. So we use that scale factor not only to find the new positions of our vertices, but also we can use it to calculate the lengths of our sides in the new figures. Looking at it algebraically, if you have vertices at any coordinate x, y, and you are told to enlarge it by a certain factor, all we do is we multiply each of the x and the y values by that number. Same thing if you are reducing. The only difference between an image getting larger and an image getting smaller, or being reduced, is the value of that k. If k is bigger than 1, something like 2 or 3 or 4, your dilation is an enlargement, meaning your figure is getting bigger. But if your k value is smaller than 1, but still positive, something like 1/2 or 1/3, then your dilation is a reduction, meaning it's getting smaller. And we'll see this played out in the next couple of slides. Example 2. Draw the image of triangle ABC after a dilation with a scale factor of 3. Identify the type of dilation. This scale factor of 3 means that k is going to equal 3. And all of your x, y values that we did have are going to become k times x and k times y. To identify the type of dilation, k is bigger than 1, therefore the dilation is an enlargement. We'll go ahead and first graph the original triangle ABC. A is here at the origin. The point B has the coordinates -2, 3. And the point C has the coordinates -1, 1. It's going to be a little bit difficult to see this triangle because the points line up so closely, but it's going to look something like this. So our new triangle is going to have the coordinates A prime, which is 3, my k value, times the old x, and 3, the k value, times the old y. B prime is going to be 3 times the old x, which is -2, and 3 times the old y, which is 3. C prime will have the coordinates 3 times -1 and 3 times 1, giving me A prime is 0, 0, B prime is -6, 9, and C prime is -3, 3. So my new triangle will still have one vertex at the origin. My next coordinate is at -6, 2, 4, 6, and then my y value is 9. It's going to be a little bit off my graph, that's fine. This is B prime. And C is -3, +3, which will be here. So again, drawing my triangle, it's going to be a very narrow triangle, but it will look something like this, where I have A prime, B prime, and C prime. Example 3. We're going to draw the image of this rectangle after a dilation with a scale factor of 0.5, or 1/2. Identify the type of dilation. Well, here k is equal to 0.5, and since k is less than 1, that means the dilation is going to be a reduction. Multiplying by a number smaller than 1 causes our figure to become smaller. So now looking at each of these coordinates, I need to find the ordered pairs. W looks like it's at -2, 1, 2, 3, 4, 5. So W is at -2, 5. X, we have 2, 4 for X and 2, 4, 5 for Y. Y is at 4 for X and -2, 4, 6, 7 for Y. And Z is -2, -7. To find our new coordinates, I need to take each of the x's and y's and multiply them by that k value of 0.5. So W prime becomes 0.5 times -2. Y becomes 0.5 times 5. This ordered pair becomes -1 and 2.5. For X, my new X is 0.5 times 4 and 0.5 times 5, which is 2 and 2.5. Y prime is 0.5 times 4 and 0.5 times -7, which becomes 2 and -3.5. And lastly, Z prime is -2 times 0.5 and -7 times 0.5, giving me a new coordinate of -1 and -3.5. Graphing these, my new figure will look as follows. So this rectangle WXYZ is my image of the original WXYZ triangle. On our last slide, go ahead and take a moment to pause the video and try on your own 3 and 4 either by yourself or with your tables. Now go ahead and take a moment to pause the video again and check your answers. You might also have had decimals for your coordinates, and that's fine. Thanks so much for watching and have a great day.